So today we're going to continue working on the Haar Transform and to see so a first instance of Lossy image compression. So on Friday, just to recap, we looked at entropy coding. And so the first point we made on entropy coding is, well, the first was the definition of the entropy. So the entropy is given by this equation here, which relates the probability of a symbol, or in our case of the histogram, we can get that probability from the histogram. And so we relate all these probabilities together and we get the entropy. So remember, okay, there's this minus sign, and here's a log 2 because we're working with bits. So the unit, if you want, for the entropy would be bits per symbol, okay? So we said basically that when you have a picture, the histogram is usually more or less flat. It's not quite flat all the time, but it has a nice spread over a whole range of different values, and that means that the entropy is usually quite high. Okay, so when you look at this picture from Lena, the entropy is computed entropy is 7.6 bits per pixel. That means that even with best efforts on coding schemes, we won't be able to compress much this picture. We looked at Hoffman, a way of getting that entropy coding. This is the subtle point I'm not so sure I came across on Friday. There's two things, okay? There's the entropy itself that only computes the best-in-class effort you can make for symbol coding. But when you want to look at the arrangements, take advantage of the arrangement of the codes, the codes themselves, okay? So if you have different symbols that always come together, you might want to take advantage of that. Then what you look at is the entropy rate, okay? So the conditional entropy. And that number is much harder to compute, okay? So we cannot really have a simple formula to compute that number. So in all the subsequent slides, I'm only looking at the actual entropy and not the entropy rates. But most algorithms that you find in zip compressions or any compression algorithm you will find, trying to make use of dictionary coding and so on, trying to be able to reuse the fact that some symbols come in together in some frequency. So something to keep in mind, okay? But as I said, we'll only be looking at the entropy because that's a much easier, I suppose, indicative version of what we have to do. Right, so these are some examples we looked at. The last point we finished was by saying that with pictures, you can look at something quite simple. You can transform the original image in such a way that you can make your entropy much better. And in this case, what we looked at was the difference between two intensities, just looking at the pixel on the left minus the current pixel minus the pixel on the left. So the difference here, okay, so why do we get something better? Is because the histogram now is more compact, and because the histogram is more compact, we know the entropy is more compact, it's lower, and therefore we can compress that better. So why is that different? So what happened there? So how come, say when you use deflate, which is one of the algorithms for entropy coding, how come we can't get that? How come this algorithm can't find that? Well, here something is interesting, okay, and something I didn't talk about on Friday, but as something worth mentioning here, that here the symbols are not any kind of symbols, okay? You can do arithmetic on the symbols, okay? So the symbols are numbers, and you can add, subtract the numbers, multiplication and so on. When you work with text, you can't really do that. I mean, it doesn't make sense to subtract B from A, okay? That doesn't really make any sense. So here, something quite different happens. So we say, look at the symbols, they are numbers, we can do special things with the numbers, and one of the things we're doing here is we're doing subtraction, okay? And be able to do arithmetic, then we're able to get much further into analysis. All right, so that's kind of a key aspect, okay? Okay, so today, now we're going to look further into that, and we're going to look at the Haar transform, which is basically what you've seen with differential coding, but extended to 2D. All right? So this is the diagram we have, okay? So you have two parts in this diagram. So the top part is the compression part, and the bottom part is the decoding part. So you start from the original picture, which is the picture I. And you're going to do some transform, okay? So that's going to be, in the previous slides what we've seen was the difference coding scheme that we transform the picture by taking this difference, okay? So we find a different representation of this picture. And that gives us y here, the symbol y. And then we're going to apply quantization, which is just a way of rounding the numbers we're going to get. And then we'll get a stream of data which has very nice properties in terms of entropy. Okay, so the entropy of that stream will be very low, and at which point you can start to apply some specific entropy coding similar to Huffman coding and so on. Okay, and this is what you have. Okay, so you generate that coded version of your transform schemes. And this is your final set JPEG file, okay? Then, of course, you have the decoding scheme, which is just inverse. So first you decode the entropy, you decode the entropy coder, and then you do the inverse quantization, and then you do the inverse transform, and you get back to your original picture, okay? So that's kind of what you see in 99% of all possible image, audio, video compression schemes. All right, and so now we're going to look at the Haar transform, which is one of those. So the Haar transform, this is the one in 1D, okay? And it does exactly, I say, we restart from the different schemes. So let's say you have two elements, okay? So you have an input vector of dimension 2, okay? So you have x1 and x2. And what you do to get the transform from these two is just you apply this 2x2 matrix, which is this orthogonal matrix. And as you can see, it's quite simple. So looking at the first, the results of the first, so remember it's row by column. So we'll build column by row. So we'll be looking here at, so the output y1 will be simply x1 plus x2 divided by square root of 2. Okay, so that's the first one. You take the average of the two values, and here you take the difference of the two values. Okay, so there you have two values, and you transform that into a new vector, which is just the average and the difference between these two values. You can invert that, obviously, okay, and it's quite simple. So you haven't lost anything in your transformation. Okay, the transformation transform your x into y, but you haven't lost anything in that process. All right. So to get the inverse, you apply the inverse of transformation because it's an orthogonal matrix. You can just take the transpose of that matrix, which is actually turns out to be the same here. So the x1, x2 is actually just the matrix times the y matrix. Okay, so that makes sense? All right, so it's simple transformation. So how will you go about doing that on an entire signal? Well, basically what you can do is then you can chunk your stream into pairs of two, okay? So you take you take two symbols, do the transform, look at the next two symbols, do the transform, and so on. Okay, so you split your stream, your 1D stream, into chunks of two, and then you apply this little transform for all these values. All right, so when you go to 2D, there is a nice way of doing that using matrix transformation. But basically, I'm just going to look at directly at the output of what it looks like. Okay, so say now you have a block of 4 pixels. Okay, so I have a little matrix here, and that's basically just a 2 by 2 part of my picture. Okay, so I split my pictures into blocks of 2 by 2 images. All right, so I take I tiled my pictures with these little blocks. And then I transform these blocks by saying, okay, so we have A, B, C, D, and now this is the new block, how it looks like. Okay, so the first, we look elements by elements. If you look at this one here, what you see here is you basically take the average of all the elements. Okay, so we have the intensities values are A, B, C, D, and then here we have the average or the sum of all these 4 intensities. Okay, so we call that a low filter, and that's because basically we're having a low pass filter on the picture, and it's low because we have low pass on both the x and the y axis, so we call that a low filter. All right. If we look at this element here, it's called a high-low filter, and that's because when you look in detail, what you do is you take the difference between A and B, and you do the same between C and D, and then you add both. Okay, so along the y-axis, you average along the y-axis, so that's a low-pass filter around the y-axis, and you do the difference along the x-axis, so that's a high-pass filter on the x-axis. All right, it's called a high-low. Does it make sense? Have I lost half of the people here? All right. So I say that again. This is so we take these 4 pixels as an input and we transform into these 4 pixels. We just replace that in the picture. And in this version here, the difference, we do the difference along the x direction both times and we average that. So it's a high pass along the x axis and low pass on the y-axis. And similarly here, you have high pass along the y-axis because you do A minus C and B minus D, but you average that along the x-axis, so it'll be a low-high filter. And the last one, it's basically a high-high filter because you take a high pass on the x-axis and a high pass on the y-axis, and you get the equivalent of a high-high filter. These things can be expressed with the H transform. Okay, so if you have Z transform. So if you have the Z transform here of that low filter, you can do the same representation of how it will look like for the other guys. Okay, so let's see how that looks like. Okay, on the left is the original, and on the right is the Haar transform. And I've done a bit more in the Haar transform here. I'm basically, when looking here, it's called the subband images. But basically, you see here the 4 pixels are rearranged. Okay, so you have the top left, bottom right, and so on. So what I've done here is like not only I've done that operation for every single pixel, but now I've decided because these 4 pixels corresponds to 4 different types of filtering operations, I'm going to reorganize all the pixels of the same natures into a subimage. So what I'm doing now is like I'm going to take, I could apply that on every single pairs of a little block of 2 by 2, and then I'm going to only, for instance, to look at the low image, I'm only going to keep all the pixels, I'm going to subsample for only the pixels that have this combination of the 4. Okay. So what you have here is only I've taken all these pixels that were the average of the blocks. Okay, so this is a picture of the average of all these little 2 by 2 blocks, and all these guys are pretty much dark. Okay, now it's not that interesting yet, but note something: the brightness has changed. Okay, and here it's very dark. Okay, that's because here you have negative values, and so most of the pixels are black, and some of them are a bit brighter. And here it's brighter than in here, and that is because when you look at the transform here, you have 1/2, okay, and I insist you have 1/2 and not 1/4. All right? And because you have 1/2, and you average 4 numbers, then the brightness essentially is multiplied by 2. Okay, so the contrast. So yeah, so it's something to keep in mind. Okay, you have these weird things. Anyway, if you readjust for the brightness, this is maybe a bit more. It's a bit easier to visualize. So the only difference between these two frames here is that I've rescaled these values so you can see them a bit better. So remember, mid-gray here represents 0, and it's in darker. So dark colors are negative, and bright colors are positive. And here I just divided by 2 in this case. Okay, so in the top left, what you have is a downsampled version of your image. Okay, so it makes sense. You've averaged, you applied this low filter, so this low pass filter, and we subsampled 1 pixel per blocks of 2 by 2. So basically, you have your picture reduced of divided the resolution by 2. On the top right, what you pick up is all the so you apply a high pass on the x-axis and a low pass on the y-axis. So that means that you will pick up all the vertical edges. Okay, so remember, high pass on the x-axis means if you have a vertical feature, you're going to pick it up because it will create a high gradient in x. And the bottom one here, this one is the high pass in the y-axis and low pass in the x. So you will pick up all the all the horizontal edges. And this one, okay, it's a bit harder to see. It's basically high pass and high pass, and basically it's almost the noise. Okay, all the very high level, high textures that are not directional, and so they'll be picked up the corners or all these fine details here that almost looks like noise or kind of well, they're not edges. Okay. All right. So that's the point. So this transform takes little blocks, 2 by 2 pixels, and do this transformation to the average difference and so on. And then if you split those guys, just rearrange them by these different classes, these 4 different classes, then you get this they're called sub-band images. All right. And now something is striking here. Okay, so come back to the difference coding. That when you look at this band here, so the low band, you're gonna come back to the same problem that on here. So it's just a smaller picture. Okay, but here most of the values are 0 or close to 0. Okay, so again, we come back to this idea that we transform our original signal into a new signal which has much less variety in the values. Okay, so now most of the values are actually close to 0. And it's indeed what we see when you look at the histograms. So when you look at the histogram just for the low band, so remember the low is the top left one. And the entropy is quite bad, actually. It's worse than with the original picture. It's 9.5. And the reason it's more than 8, okay, is because I'm doing arithmetic, and I'm starting to average numbers and divide by 2. So now the whole range of possible values is, okay, it's between 0 and 512. And I have all loads of values that could be actually non-integers values, okay? So actually, I've somehow expanded the number of symbols I could have in my picture, okay? So something important to note, so here you actually end up with more symbols, so your entropy actually expands. And the same applies here, okay? So high-low and low-high and high-high, in a way, you increase the number of symbols or even the range of the values, because now you go from minus 256 to 256, and with even worse, with a half integers values and so on. But despite that, despite the fact that you have these now fractional values and you have more symbols, somehow the entropy is lower. Okay, so we go down to 6.4 here, 5.7 here, and the lowest of all is in the high band, we have 5.2, okay? Which comes back to the initial impression we had, which is here you have way more zeros in the high, so probably there you can do a lot more work in terms of entropy. Does it make sense? All right. So to compute the overall entropy, it's basically the average of all the entropies for each of the subimages. Okay, so I have 4 different entropies, and because now each of these subimages has 4 times less pixels, I just divide by 4, and I have a combined entropy of 6.7 bits per pixel. Okay. Remember, I haven't lost any information here. It's, I can revert back to where I was exactly. Right? But still, made quite a lot of progress from the original 7 points, forgot 6 or whatever bits per pixel we had originally. All right. So, all that is fine, but still not the kind of compression we're looking for. Okay. So to get further, we need to do lossy compression. So what we've done so far, because we can come back exactly to the original picture, we just transformed it, and we can inverse the transform. It's all fine, but it's called lossless compression, so we don't lose any information. And that is fine, but you don't. There's so much you can do with lossless compression. You can limit it by what we can do, and so. If you really want to achieve high compression levels, you need to quantize your picture. You need to lose some information, which is what we're going to see here. So basically, quantization is a very simple step. You take your number, and you're going to divide it by some value. Okay, so we call that Q step. And then we're going to round it, and we're going to multiply again by that number to find the nearest multiple of that quantization step we want for that number. Okay, so I mean, example, like if you have I don't know, a value of 50, okay, and your quantization step is 100, you divide 50 by 100, that's 0.5. You round that, that's say 0, and then multiply by whatever it is, so that's 0. Okay, so you quantize that. You quantize the number this way. Okay, all right, so that's quite simple. That's trivial stuff. In the next slides, okay, so a word of caution here. In the next slides, I'm using this, I can re-multiply by this number, but usually in compressions, you just preserve, you know what the value of the multiplication here, but you don't re-multiply, okay, you just keep the rounding, you just round x divided by q step. And when you do the histograms and so on, you don't usually multiply by q step. And the reason is because you want to keep all the values to be small. Okay, but that's a minor point. All right, so on the left here, you have the original image. And what I've done is I've applied a quantization step of 15. Okay, so I looked at the original picture, and for every single pixel value, I've divided by 15 the values, so they were in, as integers between 0 and 255. So I did divide by that number by 15, took the nearest integer, and multiplied then by 15. Okay, and so that kind of looks like the same image, but you can see here, you can see there is it's called banding artifacts. So you can see every time you have a gradient. Or even on top, it's probably more visible. Like it should be a smooth transition from here to here, and but it's not smooth because you have these harsh thresholds coming in. Or if you look here, you probably can see all the gray levels as bands of dark gray and different values of gray, and this is bright gray. Okay. So this classic effect. By the way. I haven't done that in the beginning of the lectures, and I should have done that. It's best to use Acrobat Reader for reading these slides, because usually other PDF readers tend to interpolate the values in the pixels, between the pixels. And here you want to see, you want to see all these fine details, and Acrobat Reader is very good at just, will protect that, will preserve that information. So if you look at, if you use some other PDF readers, sometimes they will just blur and not preserve that. Okay, so I advise you to just use Acrobat Reader, okay, for viewing the slides. Anyway, so that's classic banding artifacts you have in quantized, when you just quantize as much. And here, what you have is you apply the Haar Transform, and you quantized in the Haar Transform. So, coming back, I transformed this picture to this picture, and I apply the same principle, but in this picture. So here I use a quantization step of 15. So every single number in the Haar Transform image is now divided by 15, rounded, and multiplied by 15. Okay? And if you do that, then something interesting happens is that you see the picture, it's much better, okay? So it's much harder to notice these kind of harsh banding artifacts. So if you look at the top, for instance, here you had a harsh difference between these two pixels, these two shades of gray, but here it's much more smoothed out, okay? And same here along the shoulder, it kind of runs smoothly from this point to this point. It's not perfect, okay? You can see, look in detail, there's some artifacts here and there, but you've kind of removed most of the obvious issues with that, okay? All right, I mean, it looks like here, it's just some problem with skin issues, and here it's like, you know, much smoother, all right? So that's interesting. So let's look at now what kind of histograms we get. Okay, so looking at the Haar Transform, now what we've done is we quantized all the numbers, okay, in the Haar Transform, and the histogram, it's basically, you know, if you took like the bin of the histograms, the size of the bin has increased. Okay, before it was a very, very tiny narrow bin. I was looking at all possible symbols. Now I'm going to take larger bins, and I say basically the bin size is 15. Okay, so any number that falls into 15, that's a range of 15, that's interval of 15, will be counted as one. So the histogram looks much smoother and much more simplified. But interestingly, the entropy, you can see, is much lower. Okay, so the first step is the entropy of the low is 4.6, but we know that's probably as bad as the original picture. But the high-low, low-high, and high-high is much lower. I mean, if you look at the high-high, you see 0.81 bits per pixel. Okay, so you need less than a bit per pixel in that subimage to represent that value. And that's because, I mean, it makes sense, okay? When you look at the histogram, you almost have 90% of the pixels that are actually 0, okay? So now we have this threshold, and we say if you're less than 15 away from 0, you're 0, so you have almost 90% of all the pixels that are in that band, okay? So there's only 10% of the rest to deal with, okay? So only 90% of the picture is easy to sort out. And so your entropy is much lower at this point. Okay, so on the left, so again, the original quantized, okay? So every single pixel is quantized separately. And the average entropy, the entropy for that picture is 3.7 pixels per bit, or bits per pixel, sorry. That should be swapped here. Okay, so 3.7 bits per pixel. When you apply this Haar Transform and apply the quantization, and what you see here, the inverse transformation, the entropy is 2 bits per pixel. Okay, so we've reduced quite a lot the domain. Okay, so that's pretty good. So now we're almost like, you know, at 2 bits per pixel, and we can see a bit some artifacts, but it's not so bad. Okay. Another thing here, you have almost 4 bits per pixel, but you still have quite a lot of visible artifacts. Okay, and now you go down to 2 bits per pixel, and you almost have no artifacts or visible artifacts. All right, so that's pretty good. All right, so what we've seen here is a simple trick. Okay, so what we've done is level 1 of the Haar transform. Okay, so we've done these guys, and remember we have this low band, so we can recognize as a sub picture here. I could say, well, why not keep on going? Okay, so we know that here the entropy is quite high in the low band, but we know we have a transform that we can apply to that. Okay, so we can recursively apply that to the next level and say, let's take the low band and apply this Haar transform. And you start doing that, and you can see now you have the high pass on this low band, and you have this other horizontal vertical high pass filters here. And you can say, well, we have a picture here, so we can apply that to a next level and keep on going like that. Okay. Obviously, at some point, it doesn't make sense to do that anymore because you're going to reach a point where the high pass or even these passes are not much more low entropy than what you have to start with. Okay, but the idea here is like you see 3 levels of the of the Haar transfer. Again, the brightness and contrast have been changed. Okay, so remember in the real Haar transform, these guys are black, and these guys much brighter. Okay, and then if you had to go for 2 level, then it would be even brighter and so on. Okay, but here's just for your own representation. Okay, so let's see if we can see that. I'd like to switch off the main lights, if you mind. All right, so on the left, you have the level 1 of Haar. And remember, you can still see some artifacts. Okay, so if you look here carefully, you can still see it's not totally smooth. You still have some quantized steps showing up. Okay, if you look carefully, you have little blocks, 2 by 2 little blocks that are kind of showing up. Okay. Anyway, so if you apply level 4 of the Haar, then it's very hard. Right, let's do that. Okay, so this is the level you have. Okay, so level 1, usually the blocks now are 2 by 2 mostly. Okay, and if you see any quantization error, they will show up as 2 by 2 blocks. Okay, so you can see in the skin. Where you can see here, you have these little patterns, checkerboard pattern, very subtle here. Anyway, now when you look at 4-level Haar, the blocks now are bigger. Okay, so you can take larger regions and quantize over larger regions. And that is because now when you do the quantization on a multi-scale level, basically a little 2 by 2 block or even a pixel on the 3rd level actually corresponds to a region of maybe 8 by 8 or 16 by 16 pixels. Okay, so when you quantize now, you quantize for pixels that actually corresponds to maybe the average over a 16 by 16 region. Okay, so so you'll have now much bigger blocks like that appearing and being totally flat. But importantly, all the fine details here in the textures are somehow, well, not all of them, but they're kind of preserved more or less. Okay. All right, so that's a bit subtle, but I mean, this is the kind of difference you're looking at now when you're comparing different compression levels. So let's look. Okay, so the quantization of level 1 is, so the quantization step is the same for both, so for level 1 and level 4. And if you look at the root mean square error, so the average of the error between the ground truth, the input image, and the quantized image now. So the error is an average 3.6 levels per pixel on the left, and 3.5 on the right. Okay, so that means that somehow the level 4 Haar allows you to preserve a tiny bit more of the picture than level 1. Oh yeah, now here's a good example of where the difference happens. As you see here, you can see these big chunks of edges, okay? Yes?
Why is it that you only apply the second order level Haar transform to
the smaller?
subband?
Yes, the low one. Because the other ones are already quite, you don't get anything from that, okay? The other ones are already transformed. So the entropy is already much lower. So you don't get, you can do that experience, you have the code tomorrow for that, hopefully. But you don't get much more to apply the Haar transform on these subbands, especially the high. I mean, the high is already, the trick of this transform, okay, is to try to transform to something which comes down almost to noise. Okay, so if you had some white noise level where you can't make up any structure in it, then you know you can't go further than that. And that's the whole point of compression. You want to go down to a stream of data which is, has all the statistics of just noise. Right? And when you apply this the high band, for instance, you're really close to that, so it's kind of hard to get anything from there. What you want to apply, you transform it on the low one where the entropy is still quite high and there's quite a lot to be saved there. All right, so you can see here, that's the one level, so you're still not able to get, basically the problem with the first level, the Haar transform, because you only look at 2x2 pixels, if you have a gradient which is much smoother and spans over a wider region, it won't pick up on that, okay? And so here, you still will, you still have these banding artifacts, so these regions that are clearly, you can see clearly a difference, whereas in the low part, does a better job at understanding, okay, the gradient is smooth over a whole region of maybe 16 pixels wide, and therefore you can smooth out the ramp over the 16 pixels. Subtle differences, okay? Okay, so similar here, so if you rank up the quantization, then the error becomes more noticeable. And, again, here clearly, so this is one level, you can see clearly the artifacts are visible, whereas here on the 4 level, it's not as bad, okay, for the same quantization level. All right, so, okay, so you had these tables, and so the way you do the things now, so you still have to average the entropies over the entire picture, but now the sub-images become smaller and smaller, okay? So you kind of have these kind of tables where you organize, so you have the level 1 where you have these sub-images, and so the low, high, low, high, and you have the entropy for these sub-images, and here you have how much of this, you see on the proportion of the proportion of that picture for the rest of on the entire picture. Okay, so this sub-image takes a fourth of the entire picture, and now the low image has been replaced by this level 2. Okay, so all these numbers here, they correspond to the transform of the low band of level 1. And these guys, so it shows like now it's the 16th of the entire area of the picture, and you can see entropy for each of the subbands here. All right, and you can keep on going like that. So, okay, so you can, take the low from the second level, expand that into into these 4 further subbands from this stuff. All right, so this is a kind of a graph that shows the evolution for the number of Haar levels you have. Okay, so you start here with so you start from a quantization step of 15. Okay, and so we say if you don't do any Haar transform, you get 3.7 or something like that of entropy. So that's your level 0 of the Haar transform. So you don't apply Haar transform, just take the entropy of your quantized image. Then level 1, so you apply the Haar transform, you have your 4 sub-images, and this is how you have a level of 2.1 of entropy, and this is the budget taken by each of the subbands in terms of entropy. Okay, so the low subband takes most of the entropy here. And you can see, okay, you can transform that into these 4 other subbands, and then you can take this low level again and further compress that and keep on going like that. All right. And you see, okay, there's kind of diminishing returns here. I mean, sure, from 4 to 5, from 4 to 3, you gain a bit, but it's marginal. All right, so this is kind of the core of, so what we've seen here was the core of all the image compression algorithms, okay? And basically, when you look back at what JPEG does, it basically does the same with a number of other things, okay? We'll do that with a different transform, and as we'll see, we'll do more psychovisual, more human perception tricks there. All right, but somehow, okay, when you apply the quantization, when you apply the Huffman transform, okay, so the entropy coding on the pictures you get after quantization, somehow you get quite a substantial discrepancy between the result you get from the theoretical entropy you should get. Okay, so basically, so if you look at 1 here, so 1 is the original image, and we know from the ideal entropy we should get 3.7 or 6. So that's a quantized image, no Haar transform. And here on the second column here, what you get is the Huffman after Huffman coding. So you apply Huffman and you look at what you actually got in terms of bits per pixel. And you see you have something quite close. I forgot what it is, like, it's 3.7, okay? So you have a bit of a differential between the ideal number that entropy tells you and the actual coding you have from Huffman, but it's not too bad. When you apply Haar, you can see that it's not great, okay? This is the ideal. The ideal tells you it's like a 1.6 or something like that. And Huffman tells you, after applying Huffman, you actually get only something like 1.7, okay? So actually it's quite a bit of a gap. And the reason why you have that, it's because Huffman is not actually ideal at that point, okay? So Huffman is really not what you want to. You need to do a little trick to get back close to the entropy. All right, so remember, Huffman is just a good algorithm to get close to the entropy, but you're not guaranteed to be exactly at the entropy level. And the reason why Huffman is a problem is because you cannot really have, if you have a symbol, okay, so Huffman is not very good if you have one symbol that is extremely frequent. So if you have a picture that is totally white, for instance, okay, and then there's only, you do the tree, you do the Huffman tree, and it would say, well, you just need 1 bit to express the color, okay, because you just need to say there's ones everywhere or zeros everywhere. So fine, so you have 1 bit per pixel. But really, because you only have one pixel for the entire picture, you know that if you do random length encoding, you'll save quite a lot of more of in terms of compression, right? Because the optimal entropy number is a number of bits per pixel which is much less than 1. All right, so it's say maybe the number of bits per pixel you have is say 0.1. Okay, so if you say the optimal entropy is 0.1, how do you go about doing that in Huffman? Huffman, you're limited. You still use at least 1 bit for a symbol. Okay, and so to go below 1 bit is a bit of an issue. You need to do something else. And that's where using the random-less encoding schemes we talked about. So where we were? Yeah, this one. Okay. So to say if you have one symbol that is used multiple times in a row, then you just count the number of times it's happening. You replace that number of occurrences in your stream. That kind of situation is very good if you have one symbol that is used very frequently, because then you know you have very long strings of sequences of when you just have these symbols. Okay, so typically here we have the symbol 0 quite a lot, especially in the high band. You have loads of zeros everywhere, so we want to be able to say the whole, we have 15 pixels in a row that are 0, so we don't want to have to, we want to just say ahead, okay, next 15 pixels are 0. And that's, this is quite an important point, okay? So Huffman alone usually is not good enough because one of the symbols is very frequent, and that's a 0. And therefore you use run length encoding to get a bit further. All right, so this is the point, okay? So if you apply just Huffman, you get still quite a gap here, but if you apply run length encoding, you get almost no gap, and you kind of close the bridge with theoretical numbers. All right, so this is what I said here. Okay, so this coding scheme is slightly different from the one where we just mentioned. Okay, so I'll just go through a tiny bit detail. It's something that was supposed to divide mainly for compression. So you have your sequence here of numbers, and as they appear in your transform quantized image, and you see you have a whole string of zeros, and so you'll do this random length encoding, but just for the zeros. Okay, and you introduce basically a number of new symbols. So you still have your whatever integers you have are just their own symbols, but now you have these symbols that are 4 zeros in a row, or 2 zeros in a row, or 8 zeros in a row, and so on. And you can use now these symbols in addition of the other symbols you have, and by just adding these new symbols, you'll be able to get much better compression. Right, so this is really at the heart of it, okay? This is the picture you get for compression, okay? Your initial picture, you do a transform, and here it's with energy compression, because really what happens, like you have all the signals compacted into one part of the picture, and then you apply quantization, and quantization you apply entropy coding. Things we haven't done yet, and that's kind of remarkable, okay? Here we haven't looked at, like the picture looks better, and that's because they are better. When you look at the, objectively, when you look at the, any of the objective metrics we had, so they will be better, okay? So doing this Haar transform, what it does is really rely on deep, coming back to the Brownian motion example I gave, okay? So you have the stock market, it's really at the heart of it, there's this process that tells you whether you go up and down, okay? So the process, that's the underlying process. And so therefore the entropy was much smaller than what you see in the signal, and you have a way of generating that. So you had a good model, a simple model to explain that signal. And here, what we have is the Haar transform is a bit like that. It's kind of a way of saying, this is a better representation of your pictures. Pictures really are more kind of presented as a Haar transform, where you look at nearby pixels that usually are similar to each other, okay? So that's kind of the key here. What you're looking here at the statistics of all the pictures, and the transform gives you a better model for what a picture is than just looking at the pixels at a bunch of values. And because you do that, then what you get after transform and quantization is actually better looking pictures than you had before, like closer than the without transform. Okay? But we haven't yet introduced any notion of human visual systems and so on. Okay? So the perception, all the stuff we know about perception from the first course first lecture we had, we haven't integrated into that. Okay? It's not like just it's perceived to be better. It is perceived to be better, but that's as well because it's objectively better. Okay? The whole part after is on how you do things to make sure that there's the perception and there's the objective metrics, and we're trying to optimize for the perception of it. Trying to make pictures that look compression, like trying to take advantage of the human flows. All right, that's it.